Hello students, let us proceed further with our discussion on the module 2. Now we are into the last part of module 2. In the today's session, let us continue our discussion with BIOS Int 10H programming, DOS Int 21H programming, and I will conclude module 2 with a discussion on interrupts of x86 processors or PC. Now, in this session, we will be in detail discussing on some of the programming aspects of BIOS Int 10H, where we try to write some codes for clearing the screen, setting the cursor position, writing characters to the screen in text mode, drawing lines on the screen using graphics mode, and changing the video modes. With respect to DOS Interrupt 21H, we will have a couple of examples on inputting characters from the keyboard. It could be a single character or it could be a string, outputting characters onto the screen, and outputting of strings. At the end, we shall wind up our discussion with interrupts in x86 PC. Now, in the last class, I had given you an hint on what is this interrupt. Interrupt in any microprocessor basically is used to create interaction between the internal and external or I/O devices and the processor. If the I/O devices want some service from the processor, they send a request for service through a signal, what is called as interrupt signal. In 8086, it supports totally 256 types of interrupts, where the interrupts are numbered from 00 to FFH. In 10H and in 21H are most widely used functions, specifically for some of the video related functions and inputting and outputting of, say, data onto the screen and from the keyboard. Let me directly pass on to the BIOS Int 10H programming. In the last class, we discussed what is the need of these BIOS and DOS interrupts. Say, BIOS and DOS interrupts are basically used for creating an interaction with the hardware and the user. Now, I would like to rewrite the same picture what we had discussed in the last class. This is your hardware. Above this is what is your BIOS. Above this is what is your DOS. And then you have your system program, and then you have your user program. So, user program calls a system program function, in turn it calls an operating system function, and it may call a BIOS function, and this BIOS function in turn helps us in accessing the hardware. Hardware returns our, say, response for that call to the BIOS function, and BIOS function in turn may reply back to the DOS, and then it may reciprocate back to the system software program and then to the user program. This is one of the best and efficient way of interacting with the hardware. Now, basically BIOS is basic input output setup, which is burnt in ROM, read only memory. So, in 10H subroutines are burned into the ROM BIOS. BIOS is basic input output setup. My dear students, remember the interrupts less than 20 are called as BIOS interrupts, and interrupts greater than 20H are called DOS interrupt. Remember this throughout your life. Suppose if I say int 6H, int 7H, or int 8H, or int 10H, or int 12H, all of them comes under what? They comes under BIOS interrupt. And if I have some interrupts being used in my program, and that number, say interrupt number crosses 20, that is 21 and above, say, is what is called as your DOS interrupts. Now, int 10H subroutines are basically used to communicate with the computer screen video, because majority of the programs or functions of int 10H are related to the display. It is basically used for manipulation of screen text, graphics via int 10H. How does this interrupt works? See, these interrupts are predefined programs which are stored at a particular location. whenever you call these particular interrupts, say a particular program gets executed which is pre-stored at a predefined location. Now, that particular program may give you more than one functionality. Now, if int nh, if it gives more than one functionality, then how do I select the different functionality or the functions present in int nh program? The way of selecting one of the function in int nh program is by loading appropriate value to ah, we would be able to call or refer a particular function in int nh program. Now, let me directly start with the characteristics of a monitor. Why do we need to understand this? Because int nh basically works with, say, the monitor, especially display. My dear students, please carefully understand here, say whatever the programs that I write from now on, say using int nh or int21h, in both of that I would be acting upon, or I would be controlling, or I would be modifying the attributes of the hardware. Say here the display, the monitor is an hardware, it is a resource present in the computer. As per this picture, what did I say? Say your interrupts will help us to create interaction between the user program and the hardware. It also helps us in interacting with the hardware. So using these interrupts, that is int nh, I am able to interact with the hardware, that is my display monitor, and I can change the attributes of the display monitor, which is very wonderful. Now, if I take any typical PC monitor, the monitor screen can be divided into 80 columns and 25 rows, which is in a normal text mode. So, the whole screen that you have can be divided into, say, 80 columns and 25 rows. Now, the columns are numbered from 0 to 79 and the rows are numbered from 0 to 24. If you carefully observe here, this is the leftmost corner of my screen, say, which is represented by the row and column, that is 0th row and 0th column. The top right position is represented as 0th row, 79th column. The leftmost bottom position, which is the 24th row, is represented as 24th column and 24th row and 0th column. Now 24th in the sense, since I am starting my row number from 0, it is the 25th row. So 25th row and 0th column, and appropriately, say if I go to the rightmost corner, it is 25th row and 80th column, but here it is mentioned as 2479 because I have started my row count and column count from 00. Now, let us try to understand with an example how basically we can clear the screen. In your high level language, you have something called as clear screen function. Using that clear screen function in your high level language like C or C++, you are able to clear the screen. But till date, you might have not thought of, say, who has written function for that. Till date, you have thought that, say, the compiler, the person who has written that compiler or who has developed that compiler has developed a clear screen function. Yes, I do agree, say, the developer of that C compiler or C++ compiler would have written the function for clear screen. But if you can again correlate with this particular picture, see, user program uses a clear screen, where that clear screen is a function supported by, say, C compiler, say, which is a system software. So in that clear screen system program or system function, it may be calling a DOS function or it may be calling a BIOS function so that it could access the hardware. My dear students, say till now you have worked on C, you have worked on C++, both of them are high level languages and you are trying to work at the surface level. Now in this assembly language programming, you will get a focus on how basically these high level language, say, predefined functions accesses the resources or hardware of a PC. Now here is a very good example. To clear the screen, say using int nh, we need to, say, follow certain rules and regulations, or the predefined registers has to be used and loaded with an appropriate value. Say for example, when I call int nh with ah is equal to 06h. Now see, int nh function request 06H is used for clear screen. It is nothing but, I should say, move AH comma 06H int 10H. Now, before proceeding further, I would like to give you a simple, say, illustration explanation on what is this int instruction. Int is an instruction, software instruction supported by 8086 instruction set, where the syntax for this int instruction is int nn, where this nn is the type number that we are trying to specify. Now, what is the type number that I am specifying in this int instruction? The type number that I have specified is 10H. So, before invoking this 10H interrupt, I am trying to load AH with the option number or the function request number. And what is the function request number? The function request number is 06H, where this 06H function of int 10H is specifically used for clearing the screen. Now, along with the function request, say I have made AL is equal to 00, BH is equal to 07, CX is say loaded with 0000, DH with 24 and DL with 79. What is the meaning of these values? AH06 calls the scroll function to scroll the screen upward so that you will have the cleared screen effect or clearing the screen effect. BH is equal to 07 indicates the normal attribute of the screen. AL is equal to 00 indicates that I want to clear the entire page. CH and CL register specifies the starting row and column of that particular page, and DH and DL specifies the ending row and ending column. If you carefully observe, the starting row and starting column is 00, that is the leftmost corner of the screen, and your ending row and ending column represents, say, 24 and 79, that is the rightmost corner, bottom corner of the screen, means, say, I am trying to clear the whole screen. So, before calling int 10H, I should load these registers with the appropriate value. My dear students, please remember, if you ask me a question, sir, instead of using BH, I will use BL with 07, sir, what will happen? See, these are all predefined service routines. I call them as interrupt service routines, or it is basically called as interrupt service routines. Say, where these service routines are predefined programs, say, used to service a particular type of interrupt. Now, if I want to clear the screen, say already this is a program which is being burnt in the BIOS, where, say, in this int 10H I have function 06H which works, or which is made to work for this predefined contents of the register. Suppose if you don't load BH with the appropriate value, it will take the current content of BH and it works for that. So, you should be very careful while calling an interrupt. So, it is very important to preload these registers or the corresponding registers with an appropriate value. Now, here is the code for clearing the screen. Move AH comma 06H, move AL comma 00, move BH comma 07H, move CL comma, I am sorry, it is move CX comma 000H, and move DX comma 2479H, say ending row and ending column in 10H. I am invoking the interrupt. Now, we have understood how to clear the screen. Now, let us try to understand how to set the cursor's position. Now, when I am able to have control on the screen, that is the hardware resource of your computer, let me go one step ahead. Say there is a cursor which will be generally blinking in the leftmost corner when you open up the screen. How about positioning that cursor onto the middle of the screen? If you ask me a question, sir, why should I do that? See, if you go to an ATM counter or in some of the applications, you wanted to display something on the center of the screen, or you want to display something on the rightmost corner, or you want to display something on the leftmost corner, or rightmost bottom, or leftmost bottom. Then how do you do that in your programming? So, you need to access the attribute of the screen, and then you should tell and control the screen that, say, whatever that I try to display should be displayed at a particular position. If that has to happen, or if the reading has to happen from that particular current cursor position, then I need to have a control on setting the cursor to a specific position, which can be done using function 02H of int 10H, where, say, I would be able to set the cursor position. See, the desired position, that is the row and column, is specified in DX, where DH will specify the row and DL will specify the column, and video RAM can have multiple pages of text. as usual, because it can support more than one page. AH will be loaded with 02, which indicates, say, the page 0 is chosen by making 00H, BH is equal to 00H. So if BH is equal to 00H, I am trying to choose the page 0, AH is equal to 02H, because that is a function request that I need to, say, call under int H. After int H as executed, those registers that are not used by the interrupts remain unchanged. Remember this. So here is a code: move AH comma 0 to H, int move BH comma 00, move DL comma 25, move DH comma 15. What is the meaning of this? So it gets set the cursor at 25th row and say 25th column and 15th row. So if this is my screen, so as per this, say DL specifies the column number and DS specifies the row number. So somewhere here it gets the cursor will be get set. So this is what is the meaning of setting the cursor at a specific location. Next, now we know how to set the cursor. So wherever I want in the screen, I should be able to set the cursor. Now assume that the cursor is blinking at some position. Say here is VTU Belagavi. Now cursor somewhere is blinking here. Now I want to get the current cursor position, and I would just want to find out where is the current cursor position. Now to do that, say we will be using, say, function request 03H. Basically your monitor will have a text mode and a graphics mode. In the text mode, say we try to determine the cursor position by using the function request 03H, where generally the page chosen will be the current viewed page. The code for this is move AH comma 03H, move BH comma 00 int H. So it gives me the current cursor position, say where the current cursor position will be given in DH and DL after execution of this particular code. Now we have seen clearing the screen, setting the cursor, and then getting the cursor position. Now let us try to change our mode from a textual mode to video mode. To change the mode of the display from a textual mode to video mode, say we will be using int H with AH is equal to 00 and AL will have the video mode. So if I specify the code value here, some different value here, that will set the video mode. Now to understand the video mode, we need to understand the different attribute of a monochrome monitor. What are all the different attributes of a monochrome monitor? An attribute is something, it is characteristics. Attribute means characteristics. The attribute associated with each character on the screen provides the information to the video circuitry. There will be a video circuitry where the attribute of each character, say, will be provided, say, to the video circuitry, where the character which is foreground, which will be displayed, and your background, where basically we will be having the color and intensity. Now the attribute byte for each character on the monochrome monitor is generally limited, because I will have only black and white. Monochrome is only black and white. Now here what will happen is, say if I take 1 byte of data, say the lower 3 bits will indicate the foreground intensity, say the D3 bit will indicate whether it is a normal intensity or an highlighted intensity, D4, D5, D6 indicates the background intensity, and D7 indicates whether the character has to be displayed as blinking and non-blinking. My dear students, in the video RAM, for every character that I display, say for example, if I want to display character A has got some value, say, so this value, say, is basically 1 byte. This value is basically 1 byte. If I take this value as 41H, which is nothing but 65, say 41H, so another byte of data will specify the attribute. So this attribute is what is being displayed on the computer screen in the slide, where this byte will specify the attribute of that particular character being displayed. Now see, the foreground intensity is for the actual character being displayed, and the remaining aspect is for the foreground only, that is whatever the character that we are trying to display. So I can also sometimes display my character in a blinking mode. You must have seen that sometimes the character on the screen will blink. So you are trying to change the attribute of the character where, say, by setting this to 0 it is non-blinking, and if you set this to 1, whatever the character that you are trying to display will be in the blinking mode. Now if you go for a CGA mode, computer graphics adapter mode, it is a common denominator for all the color monitors, where all color monitors and video circuitry are upward compatible to the CGA mode. So if you are able to understand the CGA mode, then we will be able to understand, and we will be able to put forth this discussion for any of the upward or the advanced modes, say, where here in the CGA mode, the CGA attribute byte bit definition is something shown here. We will be using RGB color. D0, D1, D2 specifies RGB for background, and D4, D5, D6 specifies RGB color for background, and D7 specifies whether it is blinking or non-blinking, and D3 specifies the foreground intensity. So this is how basically the CGA attribute byte looks like. So every bit has got something to specify about the foreground and the background. Now the background can take up to 8 different colors by combining the prime colors, your red, blue, green, RGB. The foreground can be of any different 16 colors by combining red, blue, green and intensity. So for foreground I have RGB plus intensity 4, 2 power 4 is 16. Say for background I have RGB, say, where using this RGB I would be able to specify 2 power 3 is 8 different colors for the background. Now here is a simple code for specifying an attribute of a byte in the CGA text mode. Let us take this example. Write a program to put an ASCII space 20H on the entire screen. Use high intensity white on a blue background attribute screen. So what is the prerequisite? It is a blue background screen where I need an white intensity for a space, say ASCII space, that is 20H. Move AH comma 00H, set the mode option. AL is equal to 03. CGA color text mode means, say, we will be setting the video mode here. I am calling in 10H. Move AH comma 09H, display option. What I want to display here, move BH comma 00, I have to display whatever that I want to display in page 0, move AL comma 20H. So where what is that need to be displayed is now in AL, which is ASCII value for space. So I need to display ASCII value of space. So I am trying to put the ASCII value of space in AL, and then I am loading CX with the count. So repeat it for 800H times. Move BL comma 1FH. High intensity white on blue is the attribute, say, that I am trying to give it to the background, which will be loaded into BL, and I am calling int 10H. So say first I set the video mode by specifying 03 into AL, and then I am trying to display a character on the screen. Now let us pass on one step ahead. Say we will pass to int 10H, where we are going for graphics related programming, where we try to understand the pixel resolution and color. Now in text mode, basically the screen is viewed as a matrix of rows and columns. We already know this. In graphics mode, it is a matrix of horizontal and vertical pixels. So in text mode it is row and column. Here it is, say, horizontal and vertical matrix of pixels, where the number of pixels depends on the monitor resolution and the video board. So as and when the number of pixels per screen increases, say, the resolution, the clarity also increases. The two facts associated with every pixel on the screen must be stored in the video RAM are location of the pixel and attribute of the pixel, in which position the pixel is present. The second is what is the attribute of the pixel. Say the pixel attribute is specified by the color and the intensity. As usual, higher the number of pixels and colors, larger the number of memory requirement to store them. So automatically your resolution is higher, more number of pixels per screen, say more data to be stored, say, because every data will have two attributes, that is the position of the pixel and the attribute. So automatically the memory requirement, say, increases with the resolution. Now, in a textual mode, basically it is 80 cross 25 characters. So, I will be having 80 columns and 25 rows. Totally, I will be having 2000 characters, which is nothing but 2k characters plus 2k bytes for attributes. So, if I want to store A will require 2 bytes, one for storing the value, ASCII value of A, another one is to store the attribute of character A. So, each screen, that is each frame, takes totally 4k, which results in Cga supporting a total of 4 pages of data, where each page represents one full screen. Basically, in this mode, we will be able to specify 16 colors, say in the color mode, say with respect to the textual information is concerned. Now, coming on to the graphics mode in a color monitor, basically we will be having, for a medium resolution monitor, we will have the graphics mode of 320 into 200. So, 320 into 200 gives me 64,000 pixels per screen or per frame. Dividing the total video RAM of 128k bits, assume that if I have 128k bits of video RAM, so 16k into 8 bits, which is nothing but 128k bits, say by 64,000 pixel, because I have totally 64,000 pixel, it gives me 2 bits for colors of each pixel. So, to specify the colors of each pixel, I will get 2 bits, where 2 bits give 4 possibilities, because 2 to the power 2 is 4. Thus, 320 into 200 resolution Cga can support no more than 4 colors. So, if you go for a medium resolution monitor which can give you 320 into say 200 pixels per frame, it can support maximum of 4 colors, where we will be using AL with 4 here. Now, if I go for another graphic mode of high resolution, where high resolution will give me 640 into 200, that is say 1,28,000 pixels per frame, say dividing this by 1 bit for color, which can be on a white or black. Suppose if it is black and white, so if it is on, it gives me white, if it is off, it gives me black color. So, if I specify only 1 bit to represent the color, then I can give only 2 colors. Now, 640 into 200 high resolution Cga can support only black and white. To select this mode, we will be using AL is equal to 0.6. With a fixed amount of video RAM, the number of supported color decreases as the resolution increases. If the clarity of the picture increases, say pixel increases automatically, say here the number of color supported decreases. Now, we have understood the moderate resolution, high resolution, textual mode, graphics mode monitors. This is the fundamental concept that we need to understand when we are trying to play with the monitors. Now, let us try to have a concept of pixel programming using Int NH. Now, how do we address a single pixel on the screen using Int NH is with AH is equal to 0 CH, that is function request 0 CH will help me to access this particular pixel. So, where the X, that is column, and Y, the row, coordinates of the pixel must be known to vary depending upon the monitor resolution. So, by using the value of X and Y, that is a column number and a row number of that particular pixel, I would be able to vary the pixel attributes. So, to turn on the pixel or off, say I can make AL is equal to 1 or AL is equal to 0 for making it black and white. Now, we have understood how to handle one single pixel. One pixel is one dot in the screen. Now, my dear students, please understand the power of say these BIOS and DOS interrupts. So, using BIOS and DOS interrupt, even I am able to set the attribute for a single pixel getting displayed on the screen. Then if I am able to handle say the programming at the pixel level, say I could make any type of wonder using this display. Now, let me just go one step ahead. How do I write a horizontal line, say using this Int NH programming, drawing lines in the graphics mode? To draw a horizontal line, we need to choose the row and the column values to point to the beginning of the line and increment the column until it reaches the end of the line. So I should start with the beginning of the line and then say go up to the end of the line. To draw the vertical line, increment the vertical value held in dx register and keep the cx constant. Now let us try to understand how basically we do this. Now here is a program which I have extracted from the textbook. Write a program to clear the screen, set the mode to Cga mode, that is 640 into 200 resolution, and third one, draw an horizontal line line starting at the column 100 and row 15. So what should I do? First I should clear the screen, next set the video mode, and then third draw a line. Move AX comma 0600 which will scroll the screen. Move BH comma 07H, set the screen to the normal mode. Move CX comma 000, set the row number and column number. Move DX comma 184H, that is row number and the column number. Invoke int NH so that the screen gets cleared. Then to set the video mode, move AH comma 00H. So I go for the video mode. Move AL comma 06H. 06H mode indicates which is a CGA high resolution mode as requested in the problem. I am calling the int NH. So two job is over. Clearing the screen and setting the CGA mode is over. Then let me load the count. Move CX comma 100. Start the line at the column number 100 and row number 15, where column number is given at CX and row is given at given by DX. Move H comma 0CH. Move AL comma 01H int NH. So we are trying to make the pixel wide by AL is equal to 01. I am switching on the AL, so pixel will be wide. So I am calling int NH. AH is given with 0CH, which is a function to draw the line. So I have given the column number, row number, starting column number, starting row number, and then I have given the function request. Then what is the type of the pixel that I am using for drawing the line, and I am invoking the function. Increment CX, so CX gets incremented so that it can move to the next position. Then compare CX with 200, so I should go till 200. So because I should end the writing at 200 or drawing the line at the 200th column, so the initial count of CX is 100. So now I go up till 200. If it is not 0, if it is not equal to 200, that is content of CX is not equal to 200, I go back. So this is repeated totally 100 times so that your line will be drawn. Now coming on to the DOS in 21H, this DOS in 21H is basically a disk operating system or the operating system interrupt. It is commonly referred as DOS in 21H function calls, where it is used in contrast to BIOS ROM based int NH. So wherever I use int NH, I could also use int 21H, because some of the functions in int 21H also will help me to act with or change the attribute of the display. Now let me start with the first function, DOS int 21H option 09H. So option 09H of int 21H is used for displaying the data string onto the monitor. However, before calling int 21H to display the data string, you need to load the starting address of the string to be displayed with or in DX, and A should be 09, and if you invoke int 21H, so whatever the string that is being pointed by DX get displayed on onto the screen. Now see this concept here. Message DB Sai Vidya Institute of Technology, which is a message that I want to display. Move AH comma 09H, I am invoking the function number 09 in int21. So move DX comma offset of message, where DX point to the message. So offset is an assembler directive which will help the processor to load the offset address of, that is the effective address of MSG, that is message, onto the DX. Now DX will be pointing to the starting address of this message Sai Vidya Institute of Technology. Then you call int21H. So after invoking the int21H, so you will get on the screen the message being displayed. Now we have understood that using function number 09H under int21 we will be able to display a string. Sir, suppose if I want to display a character, what should I do? To display a character onto the screen, using int21H, we have function request 02H. So function request 02H is basically used to display the character which is present in DL, to get displayed onto the screen. Carefully observe this. If I want to display the character R, move AH comma 0 to H, move DL comma ASCII value of R, say I am trying to give it in single quote, say move DL comma R in 21H. So this should be single quote, say move DL comma R in 21H. If you give it in single quote, it will take the ASCII value of R in 21H. So this option can also be used to display the dollar on the monitor as the string display option, that is 09H option will not display the string. What is this? Now if you carefully observe here, I am trying to terminate this message or the string using a dollar. Say in 8086 programming, say dollar U is used to terminate the string. When you call int21H program with function request 09H, so whatever the DX pointing to, say that message gets displayed onto the screen until and unless, say, this interrupt program come across us with a dollar. So dollar acts as string terminator. Now if you ask me a question, sir, if I don't give dollar, what will happen? It goes to the infinite loop and it keeps displaying, say, beyond, say, Sai Vidya Institute of Technology, and whatever is there, say in the next memory location, that also gets displayed. Now we know how to display a string, how to display a character, how to input a character. To input a character, we have function request 01H, where if I say move H comma 01H and int21H, so whatever the data that I type from the keyboard gets read and it will be present in AL. So after executing this particular code, so if you check the content of AL, say AL will have whatever the key that you have pressed. Suppose if I have pressed 5, say from the keyboard, so say after execution of this, say if you check AL will have 35, where 35 is the ASCII value for the input character 5. Say for example, see same thing I have mentioned here. Now option 0AH, function request 0AH. Inputting the data string from the keyboard. How do we input the data string from the keyboard? Suppose if I want to type, say, Vishweshwara Technological University, Belagavi. So to do this, say basically we will be using function request 0AH, where DX will point to the offset address of the string, say, to which the data being keyed in, say, gets stored. Now I'll directly go to the program. So here is the program, say, you know this originate. So I'm starting the program at a particular location. Data 1 is a label defined as byte. There are 6 locations. So where the first location, say, handles the count here, and then I have, say, duplicated 6 locations with FF. So what will happen is here is, say, at location 0010, the value will be 06, which is the count or the maximum length of this data buffer, and then say from 12 to 17 I'll have FF. At 11 0011H, so I'll have question mark, because I'll be storing the number of characters that I start filling up here. So move AH comma 0AH, move DX comma offset of data 1 in 21H, so which will help me to read the character, and that character will go and, say, sit in these locations. Say for example, say if I have typed ABC will go and sit here until unless I press enter. It keeps taking. Once I press enter, say, or a return key, then automatically it comes out of this, say, function loop. Now here is an example. I am just trying to put in ABC. Now if I am trying to put in ABC to this particular memory location, say total size of this buffer is 06, say total values that I have added is, actually it should be 3, because I have taken only ABC, A 41H, capital A, capital B, capital C, 41, 42, 43, 41, 42, 43 are the ASCII values for capital A, capital B, capital C, and then I have said carry as written, so which will make me to come out of this particular function. So say after execution of this particular program, if you check the contents of the memory location using debug, so you would be able to see the contents of memory location at 12, 13, 14. Assume that if I have entered ABC, so at 12 you will have, say, A, you will have B, and you will have C. Next, DOS interrupt 21H with function 07H. Inputting the character from the keyboard without echo. So suppose if I am trying to type a password, if you ask me a question, sir, I want to type the password, whatever that I type from the keyboard, if I use 02H, say, or if I use 01H, whatever that I type, it gets, say, displayed onto the screen. Then what should I do? then if you do not want to display, say, whatever that you type from the keyboard onto the screen, say for example in cases of password, then we will go for function request 07h, that is move AH comma 07h in 21h, where whatever that I try to type will go and sit in AL. So internally you can write a code to check every character present in AL after a keystroke, and then whether you can verify whether the typed password is correct or not. So this is the actual application of, say, inputting the character from the keyboard without echo. Echo means no display. Now we can also use a label to define a string buffer, so that whatever the string that we enter can get, say, pushed onto this particular buffer location. Say for example, say I have Siddharth label byte, Rohit 20, duplicate 0. The offset address assigned to Siddharth is same as the offset address of Rohit, since the label directive does not occupy any memory space. See, basically here I can have a label of type byte or double word or a quad word, where label directive can be used in the data segment to assign multiple names to the data. Now here I am trying to have a label called as Siddharth, say, where I am trying to allocate 20 memory location, say for Rohit, say, where, say, I can put some 20 data bytes, say, into this particular label. Now how do we use this label buffer? Data buffer, label bytes, maximum size of the buffer is 10, buffer count, you do not know how many locations have been filled up, buffer area db 10 duplicate 20h. Now here is a code, move ah comma 0ah, move dx comma offset of data buffer in 21h, move cl comma buffer count, move sa comma offset of buffer area. Now what will happen is, after executing of this, whatever that you try to, say, fill in will go and sit in those memory locations. Say, that is, so in this, say, buffer memory locations, the contents will get loaded, say, because your dx is pointing to this data buffer memory location. Until and unless you press enter, the data goes and sits in these buffer sizes. So the maximum size of this buffer is 10h. Now let us pass on to the last part of interrupts of this module 2, that is interrupts in 8086. Now you know what is the need of interrupts. Interrupts are basically the request, external signals which are coming from the other devices, or specifically from the IO devices, requesting for the service from the CPU. Now when a request from this from the IO devices comes to the CPU will stop the main program execution and then runs a very special routine, what is called as interrupt service routine, which is pre-stored at a specified memory location, and that location is given by a particular table, and that table is what is called as interrupt vector table. So every interrupt that is supported by a microprocessor will have an interrupt service routine which is pre-stored at a particular location. So when an interrupt comes, processor will go to that interrupt service routine, executes that interrupt service routine, and comes back to the mainline execution. So in 8086, the interrupt vector table, say, size is 1024 bytes, which can accommodate 256 bytes of interrupt ranging from int 00h to int ffh. In the beginning of the session, we have understood that 8086, say, processors starting from 8086 to 486, or say even Pentium series of processor supports 256 types of interrupts, say, where the starting addresses of these interrupts are obtained from a table what is called as interrupt vector table. So that is the reason we call 8086 supports vectored interrupts. Now what are the categories of the interrupts? The interrupt categories can be, say, called as hardware interrupts and software interrupts. Hardware interrupts are basically generated using the NMI pin and the INTR pin. NMI and INTR are the two hardware pins, say, present in 8086 microprocessor chip through which we will be able to generate, say, an hardware interrupt signals, where NMI is a non-maskable interrupt pin and INTR is a maskable interrupt pin. What is meant by non-maskable pin interrupts? A non-maskable interrupt is one which cannot be masked, means you cannot disable that, but say maskable interrupts are something which can be disabled. Now coming on to the software interrupts are basically generated using instructions like int, or it could be generated by some error condition, say for example divide by 0. So when there is a divide by 0, 8086 internally invokes a software interrupt. That is what is software interrupts. Now, how is these interrupts are related with the flag register? Now basically this is what is your flag register, where flag register is a 16-bit register. So in this we have few flags which are related with the interrupts. The flags which are related with the interrupts are IF, TF and OF. Say, let me browse through fast. IF is the interrupt flag. Say, where if you set this IF to 1, interrupts are enabled, otherwise all the interrupts are disabled. Matlab, say any interrupt coming on INTR pin will not be accepted if IF is equal to 0. TF, if it is set, 8086 accepts the single step interrupt, say that is the trap interrupt. If TF is set to 0, so 8086 works in normal mode. So this is basically for single step interrupt. OF, overflow flag, comes into picture whenever there is a signed operation and whenever there is an overflow, say it is a condition which cannot be handled by the processor, which generates an exception or an conditional error. So that is basically again related with the interrupts of 8086. Now, how basically your 8086 say handles the interrupt? Let me go to this picture. Say from this picture, whatever that I have written here, say you will be able to understand. Processor is executing the mainline program when an interrupt comes. Once the interrupt comes, processor say decrements the SP and pushes the flags, then clear the interrupt flag and clears the trap flag, say decrements SP and then say pushes CS, then it pushes IP and then fetch the ISR address. What is this ISR address? ISR address is the interrupt service routine address. So it will fetch the interrupt service routine address from the interrupt vector table, where the interrupt vector table starts from memory location 00000H. So the control of execution goes to the interrupt service routine. After executing this interrupt service routine, it pops all the registers, that is it pops IP, it pops CS, it pops flag register, say once it come across with an IRIT instruction. Remember my dear students, say for a normal functions, say the last instruction for a normal function is RET. For an interrupt service routine, the last instruction for an interrupt service routine is IRIT. Now always an interrupt service routine call is a for call, and an interrupt service routine return is always a for return. I need not have to now tell you what is a for call and a for return. Now coming on to the interrupt service, the interrupt vector table. The interrupt vector table of 8086, it starts from memory location 000 and ends at 3FFH. Totally it will have 1024 bytes, where for every type of interrupt there will be 4 bytes allocated. 2 bytes holds the content of or the value for IP and 2 bytes holds the base address. Now if you carefully see this, the first 2 bytes holds the IP, that is offset value, and the next 2 bytes holds the starting address of the segment at which the ISR for this particular type of interrupt is present. So for example, if I take type 2 interrupt starts at location 00008H, where first 2 bytes will be loaded onto IP. Say whenever the type 2 interrupt occurs, processor goes to 0008H, say first 2 bytes is copied onto IP and the next 2 bytes is copied onto CS. So CS and IP will have the new value which will point to the new code segment, and from that location say the ISR for type 2 starts and processor will execute that so that the type 2 interrupt is serviced. Now if you carefully observe this, say you have the dedicated interrupts, say these are the dedicated interrupts and these are reserved for future use and these are the available interrupts. Now what is the difference between an int and call for instruction? See, a call for instruction basically can go to any location in 1 MB, but your int can say go to a fixed location, say obtained from IVT. The second difference is call for instruction may be used by the programmer, say where based on the instruction sequence, say the call for will get executed, but when an interrupt say signal comes, we do not know when it comes. Call for cannot be masked or disabled, but int NN, that is your hardware interrupt, can be disabled. Call for pushes only the CS and IP, but int NN instruction pushes the flag register, say CS IP, and it also clears the trap flag and interrupt flag. At the end of for subroutine, you will have a for return, but at the end of an interrupt service routine, you will have the IRIT. Lastly, coming on to the functions associated with say int 00 and int 4H, which are called as the predefined interrupts. If you carefully observe, these are the dedicated interrupt pointers. So these are called as int 00H, int 01H, int 02H, int 03H, say int 04H, where int 00H is divided by 0, say single step error or a single step interrupt, non-maskable interrupt, breakpoint interrupt, and overflow interrupt. Now, int 00 comes into picture whenever you try to perform a divide by 0 operation. When you perform a divide by 0 operation, so then automatically int 00 comes into picture, then processor will automatically go to IVT at location 000 and say takes the content of IP and CS and then go to the ISR present at that location, say obtained from IVT, and executes that program. Then int 1h is for single step mode. Carefully observe, this could be a question in your say examination. Say there is no special instructions or specific instruction for setting or clearing the trap flag, but for clearing or setting the interrupt we have STI and CLI. So STI is setting the interrupt flag, CLI is clearing the interrupt flag. So but we don't have any instruction for setting or clearing the trap flag. So how can I set the trap flag? I can set the trap flag by pushing the flag register pop AX or the content of AX with this value, where D8 bit is made as 1, so that in an OR operation D8 bit is set to 1, push AX back and then pop F. So whatever that you have pushed, the updated contents, you will pop it back to say flag register so that your trap flag is set. So how do you clear the trap flag? Say by replacing this instruction using an AND instruction with this particular bit configuration, you would be able to say clear the trap flag. Now, int 2h, non-maskable interrupt. Non-maskable interrupt is an NMI pin interrupt, so which gets generated by the NMI pin and happens only when there is a catastrophic failure. Whenever there is a damaging failure happening in the system, then NMI pin gets activated. It is a high signal, so where processor goes to location 00008h and runs the ISR present, say at a location, say obtained from IVT. Lastly, int 3h is a breakpoint interrupt, say which allows the program breakpoints, which is helpful for program debugging. So your single step say basically helps in executing the program in single step mode, and your int 3h basically helps in creating the breakpoint. Assume that you have written 3000 lines code and there is some logical error. How do you debug that? Then it is better to have this int 3h after 10 or 20 lines and then start executing small portion of the code, so that you would be able to verify or review the contents of the processor registers and the memory location after the execution of the 10 or 20 lines, so that if that is appropriate, then you can remove int 3h after 20th line and then put it after 40th line and so on and so forth, so that you would be able to debug the whole code. The last predefined interrupt is int 4h, say which is generated on overflow situation. Say when we perform a signed arithmetic operation, if there is an overflow, then I can use as an instruction what is called as int2. So using an int2 instruction, say I can generate the interrupt 4, that is predefined interrupt. Overflow interrupt can be generated. Processor goes to the specific location in the IVT and then gets the say ISR for handling interrupt 4 and then runs that program. So I may get a display on the screen saying that say the data value is out of range, so which is an indication that say that ISR say interrupt on overflow got executed. My dear students, how does the address of the IVT gets calculated? Say whenever you give an instruction like say int nh, the IP value is obtained by nn into 4, then the CS address is obtained by nn into 4 plus 2. So if I give say int nn, say for example int 00h, so 00 into 4 gives me location 00000h. So at this location in the IVT I get the content for IP, and this will give me 00002h. From this location we obtain the content for CS. So this new value present in CS and IP obtained from IVT gives me the ISR location for int 00. So remember this. So the address of the interrupt service routine is obtained from the IVT by multiplying the n value, that is interrupt value, number value by 4, and then interrupt value by 4 plus 2 gives me the location say for CS in say IVT. So to recap what we have discussed today, we have discussed about the BIOS int nh programming, DOS int 21h, and we have browsed through the interrupts in x86 PC. Whatever that we have discussed for say 8086 is applicable for 8088 until your Pentium processors. Thank you very much.